Okay, so here we have web assign. Oh shoot. Web assign 8C question number 7. 0.260 kilogram block resting on a frictionless. Let's remember that. Frictionless horizontal surface attached to a spring whose force constant is 83.8 newton meters as in the figure below. A horizontal force causes the spring to stretch a distance of 6.17 centimeters from the equilibrium. Find magnitude F. Okay. So for this first part, here is a little trick you can do with the units. So we know force is measured in newtons. Now, here we are given newton meters and centimeters, which can be converted to meters. So what we can do is we can multiply our spring constant times the distance to find the force required to move at that distance. So we got if F is measured in, so F is equal to newton meters. We can just look at like the times meters. We can just look at the units right now. That's going to cancel, so then we get newtons. Force is equal to 83.8 or 6. I believe it was 8 newton meters times 6.17 centimeters, so that's 0.0617 meters, and then meters cancel like we thought. So then we get a force equal to 5.17 newtons. Okay. What is the total energy stored in the system when the spring is stretched? So, energy is, that's our potential energies. Our kinetic energies are elastic energies. So this is part A. So this is part B right now. So we need our energy. So I'm just gonna set it equal to E. Now, there is no gravity. Like the object isn't moving heights, so it won't be a potential energy. And stored in the spring when it's stretched, we can already assume that it's going to be elastic energy. So that is going to be our energy. Our energy will be equal to 1/2 our spring constant times our distance stretched squared, and that is the formula for elastic potential. So our E is equal to 1/2 our spring constant is 83.8 newton meters times our distance, which was 0.0617 meters squared. That means our energy will be equal to 0.1595. I believe the unit was joules. It was joules. And yeah, that's our answer right there. Find the magnitude of the acceleration of a block. Okay. Now this is where we can use Newton's, probably one of the core laws of physics, and that is F is equal to ma. So now we have the force. We got the force in part A, and we're given mass. Now we have to find acceleration. Acceleration is meters per second squared. So if we just simply plug in our force applied, which is 5.7 newtons, times our mass, which is equal to our mass times the acceleration, which is 0.26 kilograms, we can very simply find this acceleration, because we know newtons over kilograms is the we oftentimes use that for gravity of the planet, and that unit equivalence is meters per second squared. So then the answer would be 19.88 meters per second squared. Okay, part D. Find the speed of the block when it first reaches the equilibrium position. So here we are going to set our kinetic energy into our elastic potential energy, because energy is conserved. We know it's a frictionless surface. So I can do just label this as, this is D comes after C, yeah. So we're gonna do our kinetic is equal to our potential. So kinetic in this case would be 1/2 mass times velocity squared is equal to our potential, which is of the spring constant times distance stretched squared. Our 1/2s cancel, so mv squared is equal to kx squared. So our velocity is equal to the square root of spring constant times distance stretched all over mass. And now we can go and plug in our values. So velocity will be equal to 83.8 newton meters times 0.0617 meters squared over our mass of 0.260 kilograms. This is all over the square root, and our answer comes out to be 1.107 meters per second. This should be exactly what we got here. Now, if the surface is not frictionless but the block still reaches the equilibrium, would our answer to part D be large or small? So this is where we kind of use our common sense. If there's friction, energy is going to be lost. If energy is lost, then our velocity must decrease, because if kinetic energy is equal to energy, kinetic energy is energy. Now, if our kinetic energy decreases, one of our variables also has to decrease. The mass isn't going to decrease because of friction. I mean, if it's like maybe a very thin wood, then it would, but we're not going to go into that. It's going to have to be the velocity. What other information do you need to know to find the actual answer? Like I just said, if it's like a very a loose put together material that we're sliding, like pieces of it might come off, that could also decrease the mass. It could get stuck then in that case, which would also decrease the velocity, which would even lessen the energy. So all those kinds of reasons. That was answer part E and F. So now, what is the largest value of the coefficient of friction that would allow the block to reach the equilibrium position? So this is part F, I believe. Let me just make sure real quick. Part F. G. Oh, part G. Okay, so now this is when we start. This is when we can like recommend the force diagram. So we got FG, FN, but then we also are gonna have this this friction. Now that friction is actually going in the opposite direction. FS. Okay, and now we can use this for our force diagram because we are actually moving. Our acceleration is in this direction, which means our velocity is in this direction. Okay, so that means our static friction is going against our velocity, which means we have F. I guess it. Sorry. Okay, so then our force equation in the x direction, we don't need the y direction because they're equal, so they're going to equal to 0. So our would be F minus Fs equals our MA. And now we know our MA because our MA is the same force as in problem number 1. That is our force. That's what MA is equal to. Our mass times our acceleration. So we can go one step further before we do that actually. So Fn. So now our Fn minus an Fs is just our coefficient of friction times our normal force, which is equal to again our 5.17 value from part A. And then we can go a step further, factor out 1 minus mu. So you have 5.17. Continue to clean our house, I guess. 5.17 over our normal force, which is our normal force is mg, which then means our mu is equal to 1 minus our 5.17 value that is over our mg, because mg is equal to Fm. And we plug all this in, we should. Now here, I did get a negative sign, but mu has no units, or at least the coefficient of friction has units. You cannot have a negative coefficient of friction. Just throw in your absolute values around it, and you'll get 1.02, and that is our answer. So I think the only main thing, this one looks tough. It goes up to letter G, but I mean, there's only like 3 or 4 lines for each part. I kind of did a lot here, but like it's really simple calculations once you know what you're doing. Now I always preach like go the simple route. Like look what I did. I did unit canceling just to get my answer, and it ended up working. Sometimes you gotta think a little bit outside the box. Maybe it's not necessarily the physics part, but if you can understand what you need to do to get there, you can oftentimes fill in the blanks with physics, and all of a sudden, wow, come to a realization.